Hi, in a previous video, we've actually learned how to deal with the last case of complex roots. We learned about last case where in order to find a complementary function, we needed to deal with the case of complex roots. However, even though I hope at this moment you can get a sense of when the time path is going to be converging or not, we didn't say anything about the properties and the generally of the dynamic stability of equilibrium. And look, in order to assess each case, we will be combining what we know about second order differential equations with what we know about first order difference equations. And now, look, of course we have three cases, so let's look at each of them one by one. Okay, so first we have case number one, right? This is the case of real distinct roots. Okay, what did we say about this case? We said that complementary function in this case is equal to a1 b1t plus a2 b2t. Now, when will we have convergence? Well, convergence takes place if enough time passes and we are moving towards equilibrium, right? How do we write it formally? This is limit with t approaching infinity, yc must be equal to 0. And now look, what did we say about convergence in case of in case of first order difference equation? Well, we said that B, actually absolute value of B, of course we distinguish between oscillatory and non-oscillatory time, but this is not important at this moment, is somewhere between 0 and 1. Now, how do we need to modify our conclusion about first order difference equation when we move to the second order difference equation? Look, basically what we get over here is that if we take b to some power t, this will be getting smaller and smaller in absolute terms, of course, if b is somewhere in between 0 and 1. However, look, what if we've got a case, we've got b1t and b2t, and let's just say now that this one is between 0 and 1. However, this one is equal to 2. What is going to happen then? Of course, look, here we will have a part that with time, it's going to die out. Let's just say that this is 1 over 2. What does it mean? Our first root is going to produce, with increasing t, 1 over 4, 1 over 8, 1 over 16, 1 over 32, 1 over 64, 1 over 20, 128, and so forth. This part is going to be dying out to 0. However, what about this part? This part will be getting bigger because we will be moving to 2, 4, 8, 16, 64, and so forth. If we would have negative 2, well, then we would have 4, negative 8, 16, negative 32, 64, negative 128. So we would see that we are getting again further and further away from the equilibrium, assuming that this is our equilibrium, right? So look, the rule here is very simple, and let me just write it down once. The time path is convergent if absolute value of the dominant root is lower than 1. So, basically, when we see the solution, so we found the solution, first we must look for dominant root. What is dominant root? This is the root that is the biggest in terms of absolute value. So, if we actually got two roots, the smaller one we can simply disregard. And if it happens to be that the bigger root, so the dominant root, in absolute value is below 1, so this is the case we got. This means the time path is going to be convergent. Okay, and look, knowing this, we can quite easily extend this reasoning to all other two cases. Also just two cases. Okay, so now let's go to case number 2. So now we talk about real repeated roots. Okay, so how does complementary function look for this case? This is yc equal to a3bt, right? We've got just one root plus a4t times bt. Now, again, as it happens to be, the condition for convergence is exactly the same, right? We need to have limit with time approaching infinity going of complementary function equal to 0. However, look, again, we are encountering a similar situation that we had in case of differential equations. Because look, definitely the first condition here must be that absolute values of those roots need to be between 0 and 1, right? The argument is the same as in the previous case, right? This expression will definitely die out if the absolute value of b is between 0 and 1, right? Now, however, the second expression here is the more problematic, right? This is the case that we had also in case of differential equations, because on one hand, b to the power of t, assuming that b is between, absolute value of b is between 0 and 1, this will be getting smaller and smaller and smaller in terms of absolute value. However, t over here is getting bigger. Now look, again, we have a very similar situation as in case of differential equations. What do I mean by that? Look, if I'm gonna let's just assume that we've calculated b and it's between 0 and 1. So we know that this part is going to die out to 0, right? This is actually what we wanted. Now, the question is about the other part. So let's keep this part and let's just calculate limit of, with t approaching infinity, out of a for t times b to the power times b to the power of t. Now look, would not change anything here if I would write this in this form, right? It's the same expression. But look, if I'm going to write it this way, I can use the hospital rule, right? The rule here was very, very simple, right? Limit of a quotient is equal to limit of quotient of derivatives, right? So I can simply calculate derivatives of both of these expressions with respect to time. I can calculate derivatives and calculate just the limit of this, right? So derivative of this is just a4. So this is a constant actually. And over of this, well, the minus go up front, right? So we've got negative L and B, right? Because we need to have L and B when we differentiate the expression where B is different than E. And times B to the power negative to B to the power negative T. And look, actually this is enough. We could assess this expression. But let's go further. Let's use the hospital rule again. So we differentiate numerator and denominator again. So we got 0 divided by minus 1 goes in front, ln b times b to the power negative t. However, this is simply equal to limit with t approaching infinity out of ln b times b to the power of t. And look, what we are getting over here is a constant, of course, square. I'm sorry, because this constant will reappear, square, but it's still just a constant. This is still just a constant, and we've got the same expression as over here, right? We've ended up with exactly the same expression. We've got constant over here, a3. This constant over here is ln b squared. But of course, the properties are the same. Constants do not affect values of the limit. However, this is going to be equal to 0 if and only if absolute value of b is somewhere between 0 and 1. So look, actually, in this case, the convergence is assured in the same way as we had in case of differential equations. So, as long as, of course, now roots don't need to be negative, they need to be absolute, their absolute values need to be between 0 and 1. If those values are in between 0 and 1, we can be sure that we're going to have convergence. And this leaves us with the last case. Well, the last case, of course, is the case of the complex roots. And as usual, and as the name suggests, the complex roots are complex, so probably assessing the convergence of the time path would be really, really hard. However, in this case, it turns out that assessing the convergence of the time path under complex roots is the easiest of all three cases. Okay, look, our complementary function is given by RT, A5 cosine, cosine theta, t plus sine A6, sine theta t. Right? Now look, again, of course, the limit approaching infinity out of yc equal to 0 means that we've got convergence, right? Now let's look at this expression that we've got over here. What is here inside? Look, this is the combination of two sine and cosine functions, right? So actually, again, what will we have over here is this pattern, circular pattern of repetition. Of course, because we remember that those are difference equations, we will see those in the following form. So just as points. So this part does not affect the value of the limit. Look, it's a very similar case as we get here with the constant. Even though this expression is changing over time, it's changing in a repetitive manner. What does it mean is that if we're gonna allow time, if we wouldn't have this RT over here, and we would allow the time to go to infinity, we would observe the same pattern repeating over and over and over forever. However, there is a scaling expression that we've got over here. This is R. And look, R, as we've already said, is equal to square root of A2. As long as we have a case of complex roots, so assuming A1 squared is lower than 4A2, this is the formula for the root. And look, if it happens to be that R is between this absolute value of R is somewhere in between 0 and 1, we're going to have a convergence, right? But just let's remember one very important thing. A square root of A2 cannot be negative, otherwise we would have to deal with the complex numbers again. However, remember, I already told you that in the case of complex roots, A2 must be positive. If A2 is negative, then 4A2 is definitely going to be smaller than A1 squared, which at the lowest can be equal to 0. So look, what if I just take out the absolute value? And this is why I was telling you that this case actually happens to be the easiest. Because if it happens to be that R is lower than 1, which of course means it's somewhere between 0 and 1, we will have convergence. And this is the requirement for the convergence that we've got. Okay, now the graphs for this. Look, I can honestly tell you that I would love to do nothing more than to draw you each of these cases. However, if you're not a computer, it's really, really hard to do. This is why I decided to do a computer thing, and I prepared the graphs for you for all these cases, and you can find them on the site. Okay, so this is it. We've been introduced into the world of second order difference equations. We know how to find equilibrium solutions and how to find complementary functions under all three possible cases. So of course, the next step are economic applications. And this is what we're going to do in our next video. In the next video, we're going to turn into Samuelson accelerator, multiplier acceleration model, which actually going to provide some interesting insights to you. Why? Look, you were learning about Keynesian cross model in your macroeconomics class. We were discussing various forms of this model in case of introduction to economic analysis. However, look, we've never dealt with the dynamic version of this model, and this is what we're going to do in our next video. We're going to take Keynesian cross model, we're going to make it dynamic, and what we're going to see is that this dynamic model, dynamic version of the Keynesian cross, so national income model, is going to produce business cycle fluctuations as a result of interaction between multiplier and accelerator. And the details we will explain in the next video. Thank you for your attention.